All right, greetings. My name is Thomas Cullum. I'm from the University of Adelaide in Australia. I'm here to represent the Southern Hemisphere because someone has to. I'll be giving a brief overview of the various mission aspects of my proposed Gemini mission design. Briefly going through some of the overview of the equipment at the start, overview of the schedule, costing, and operations, and then going into some detail of the subsystems given time, and then hopefully I'll leave some time left over for questions. Thank you. Right. So I'm the only member of my team. To start with, I got bored in the summer, and this is my misuse of time. I'm a final year engineering student studying mechatronic engineering while specializing into space vehicle design and acoustic engineering, and I'm an avid space and Mars enthusiast. The Gemini Mars mission is just a basic flyby and return of crew past Mars, with the requirement that it needs to be lifted off and underway by 2024, and is requested that it is done as cheaply, safely, and simply as possible. What this really means, though, is that it's a mission to prove that interplanetary travel is possible now, and we need some way of paving the way for future Mars missions. This is sort of akin to a Apollo 8 style mission that eventually led to the moon landings. The concept of this is to mainly use proven technologies and hardware and not use new design concepts to avoid additional money and R&D, and to ensure that the system is reliable enough for usage. The Gemini direct design philosophy is based on the principle that we should be using a mixture of the ideas from the Mars Direct mission plan and the Gemini missions, with the main aims to be maximizing the mission benefits, because there's no point going if you're not going to get anything out of it. Maximize the flexibility. This sort of mission has been proposed several times before but has never gotten off the ground, in partial due to inflexible launch trajectories. We need to prioritize the system reliability of the systems and minimize the risks to the crew. These risks are the big main ones being zero gravity and the various detrimental effects to health of the astronauts, radiation, both cosmic and solar, and as well as human factors as proven in the Mars 500 report with boredom and psychological factors. So to begin with, the trajectory that I chose to use is a simple 2-year free trajectory. This provides us 2 opportunities every 26 months, which is constant and repeating. This minimizes the propulsion needs, maximizes the flexibility of the mission, and also minimizes some of the hazards coming from solar radiation as well, and reduce the complexity of the mission by reducing all the burns down to one single one just to leave Earth orbit. Using the NASA's trajectory planner, we looked at the prime trajectory windows that would be available for a mission like this, and we found that there was 4 main areas, main periods of time when we could use this as expected. This will allow us that if we miss the first 2 windows, we can potentially lay it off until 2022 and then on to 2023. Using these, we can also find out some basic worst case numbers. The longest duration for the mission is 720 days, with some of the other trajectories being slightly shorter. We have a max injection delta V when we leave Earth of about 4.4 kilometers per second, and a maximum mission delta V of 4.65. And finally, the maximum return speed, which is a rather brisk 15 kilometers per second, but that's the worst case one. Most of the other trajectories there are actually a lot less, in the 11 or 12 kilometers per second. Our overview of our spacecraft is composed of several components. The main spacecraft is composed of 3, the Earth return vehicle, which we'll use SpaceX Dragon 2, a habitat, which is a repurposed, multi-purpose logistics module, and a service module made out of a modified automated transfer vehicle. To move all this stuff out of Earth orbit, we shall be using Proton M upper stages, and using Falcon Heavy and Falcon 9 rockets to launch everything to LEO. A quick layout and rundown of how all this would work. To start with, we'd be launching a single Proton third stage booster into low Earth orbit via Falcon Heavy. This comes with some docking equipment and support facilities like solar panels and communications. Next step of the plan is to do it again and then dock the two together. And this provides the basis of our launch stack. The third step, we launch most of the spacecraft. We launch the service module and the habitat, but we also launch a Proton M fourth stage fuel tank without any of its engines or support facilities. This fuel tank is to dock onto the back of the one of the third stages and provide additional fuel to it. When this is all ready and completed and tested, we can then launch the crew up via Falcon 9 rocket with the Earth return vehicle. Once the Earth return vehicle is docked, we discard the onboard service module as we don't actually need it for the mission. Once we're satisfied that everything is complete and the suitable trajectory window has opened, we then depart Earth using the launch stack. We first use the first stage, which is just one Proton M booster. This puts us into an elliptical orbit, and then we finish it off by using the combined fuel from a third and fourth stage tank. Now that we're on our way, we are going to use the third and fourth stage to act as a counterbalance and use a tethering system to provide artificial gravity to the crew on the journey. And the way we go about doing this, we break it into a few little steps. To start with, we begin with a very gentle roll along the longitudinal axis and then decouple the booster. A small rocket or a lever arm provides a small nudge to push the booster stages off axis, and then through centrifugal force we'll pull the boosters off to the side where the tether has already been attached to the body of the spacecraft. Once this is in position and stops wobbling around, we then continue the spin and slowly extend out the 400-meter long tether till its full length. At the final, once this is completed, we just do a couple attitude control burns to make sure the spacecraft is orientated correctly and that the spin is at the full speed. That way we get the suitable amount of gravity that we desire. Step 7 is really simple. This is just our voyage from Earth past Mars and then coming back. And on step 8, we finish off by discarding the spacecraft with the crew boarding into the Earth return vehicle and then performing an aero capture maneuver first to slow us down. We can't directly re-enter when we come in at 15 kilometers per second. So we use lifting body aero braking to just put the ERV into an elliptical orbit and then come for a second pass to finish off the deorbit. Here we have a mass overview of the various systems and where all of our mass is going. These are all based on the equipment we plan on using, with the exception of the crew and science equipment, which is effectively what we've got left over budgeted-wise, which can be either crew amenities, science experiments, or various other things. The time frame for this is reasonably straightforward. It starts with an organizational phase that will last between 3 and 6 months, and this includes the commencement of the astronaut selection and training program. This is mainly just to organize the program and get all the international cooperating groups together, as we're using a vast amount of international equipment. The design build phase includes modifications to the various systems that we'll need, as well as the construction of those. Once this is complete, we will then launch them over the span of 2 months using the layout of launch vehicles I have explained earlier, as well as 1 month of orbital testing before we send up the crew. Once the crew is docked and final checks completed, the mission duration then lasts for up to just under 2 years, with various backups that last over 3.5 years potentially. This is a rough cost evaluation for these various phases based on previous costs for these modules and the various equipment and training of astronauts for previous space missions. As you can see, this adds up to $4.4 billion roughly, but we want to give it a little extra 15% just to make sure we cover everything. This works out to be approximately $1 billion each year over the span of 5 years, which is the minimum program length we're looking at. And this is quite easily accountable, as NASA's budget is between $17 and $20 billion, so we use about 5 to 6%. Our choices for Earth return vehicles are fairly limited. We required something that would be able to provide transport for the astronauts from Earth to the spacecraft in orbit and then back down again, whilst also being able to handle those high-speed and return trajectories. Because of this, we only really had two options, being the Orion and the SpaceX module. We decided to use the Dragon module instead, as this is a much lighter spacecraft and its components have been flown more frequently and more often. It's a similar story with the habitat. We required a very large volume to mass ratio, something that gives us plenty of room for the astronauts to work with. We basically came down to two options, which are ISS Drive module. We are using the multi-purpose logistics module, as this is a really simple module that requires very little modification to get to work, or inflatable habitats. Inflatable habitats were discarded, as this would make designing the gravity system incredibly difficult and probably impossible. The service module is the part that will mostly be modified. Again, our options were orbital automated transfer vehicle or Orion service module. Both of these would have, in theory, have worked, but we went with the automated transfer vehicle, as this has a pressurized area that we can use to expand the living room for the astronauts. The boosters we're planning on using for departure are based off of the Proton M's third and fourth stages and use a hypergolic fuel. The advantages of this is they're stowable, so if we get everything in orbit, however a test shows there's a fault or something where we need to delay the launch, we could potentially leave this equipment in orbit and wait for the next launch trajectory to come around. This then provides the meat of the Delta V we need for our mission, which provides us with the injection trajectory as well as some course correction fuel along the way, and is used for our counterweight. Here's a list of the various modifications we do to some of the core systems. As stated, we'd be ejecting the service module off the ERV, and we will be using the ERV mainly as the sleeping quarters and command center for the spacecraft. The habitat and service modules will need an additional docking port added, as the MPLM doesn't have two ports, it's only got one at the moment, as well as some structural reinforcement along the long axis due to the gravity we're generating. And as I've said, we're using docking systems on those boosters as well as a tethering subsystem. To launch all this, we need to be able to lift at least 50 tons to low Earth orbit. That's the mass of a Proton third stage when it's fully fueled. Could be slightly less depending on modifications to the design or use of orbital refueling, but this added unnecessary complexity to it. So our options came down to the Space Launch System and its various configurations, or Falcon Heavies, to which we chose Falcon Heavies as the hardware has been flown almost in its entirety, just not all put together. And as I've said, to launch the crew and Earth return vehicle, we use a Falcon 9 rocket. So Tether is the only part of the mission that hasn't actually flown before. It's based on a design done by Professor R.P. Hoyt and his associate. It's to be at least 400 meters long and 2 meters in diameter. Because of the mass difference between the empty booster stages and the spacecraft, this will produce a long spin arm of about 86 meters. We'll be using 20 primary lines, which are those slightly darker ones on the diagram. Each of these has 2 secondary lines that connect to the neighboring primary lines every 2 meters. This and is loaded at 75% of the maximum loading that we want. This provides us with an effective safety factor of 2.5, which is comparable to the safety factors we use for construction cranes. The design for the tether is currently designed out of steel wire at 1450 megapascals, but in theory, higher tensile materials could be used, and lighter materials, again, could also be used. If we wanted just a Martian gravity, which would provide us with a unique research opportunity, it would weigh approximately 400 kilograms and would be spun at 2 revolutions per minute. However, if we wanted to maximize the safety of the astronauts and potentially expand our research goals, we could increase this up to 1 ton and provide a full 1G gravity load, which is then spun up to 3 RPM. This would be a slightly longer tether, but it's very easily quite capable of doing. And that graph there just shows the survival probability of a Hoy tether compared to a single line tether and why we're using it. So just some clarification on how we actually spin the spacecraft. The main goal of this is to aim the service module so that it's always pointing towards the sun, and we rotate around an axis that's always pointing towards the sun as well. This means that Earth is always underneath the spacecraft and always allows us for our line of sight communications, except for when we're behind the sun. It minimizes the artificial gravity problems. Previous tests with using artificial gravity have shown that astronauts tend to get disorientated if the gravity changes when they move left or right or up and down. But because of the layout of the spacecraft, they're only moving parallel to the axis of rotation and thus will not suffer any changes to the gravity while they're going about their daily routines. This also minimizes the crew's exposure to solar radiation, as we now have them well behind the service module, which is filled with water and fuel, which acts as a buffer to any solar radiation that will be passing through the spacecraft. In the event of a solar flare, the crew will fall back to the Earth return vehicle and bolt down the internal hatches and provide even more buffering area for solar radiation. The big reason for going for a tethered gravity design is to help with our research and science. A big thing we're not quite certain of is how humans react under a Martian gravity load, and this is a big concern for a Mars mission. So in order to prepare ourselves for a future Mars mission, it seemed prudent to design a spacecraft that we would be allowed to test to see how human physiology deals with a lower gravity, and potentially vary that into finding that sweet spot in which we have a minimum gravity load that a human body can withstand without vastly detrimental health effects.
5 minutes.
No problem. We'll also look at, We'll also be looking at how food grows in this sort of gravity, as well as radiation monitoring. To deal with human factors and their mitigation, we're trying to make the spacecraft as comfortable to the astronauts as possible. So we need to make the spacecraft feel more like a home rather than a lab or a gym. One of these to do with this is to have frequent contact with Earth and frequent communication with members of the human race aside from their partner in the spacecraft, as well as encouraging them their hobbies and interests on the crew. Keeping the crew busy and moving is essential to their psychological health, as we have discovered that through the Mars 500 program, that boredom is a real danger for crews going along. And of course, have a window. Astronauts love windows. So quick overview of some of the systems before I run out of time. The life support system is based on the ISS system. It's smaller scale to deal with only 2 astronauts rather than 6. We're building in redundancy by using modular components that are used everywhere throughout the design rather than different ones. So we have one type of valve that is used for basically everything, or one type of pump that's used for everything. This allows us to have plenty of spare parts along and allow for the crew to repair things should something happen. We'll also be adding a saboteur reaction to it. This helps us remove carbon dioxide from the atmosphere, as well as allowing us to regenerate more water. Speaking of water, we're going to need a lot of it. We need about 4.2 tons for both for the astronauts to survive. Some of this water will be electrolyzed for the oxygen of the crew. There's also on board nitrogen tanks to help balance things out. At the moment, the water reclamation cycle on the ISS is at 75%, but this is potentially going to be improved if as bone loss will not be as much of an issue if we have gravity. And the saboteur reaction is given a really pessimistic 50%, but is likely to be higher. When it comes to food, we're going to pack about 700 kilograms of it, a mixture of wet and dry, reheatable and rehydratable meals ready to eat. As well as we are looking into growing some fresh foods grown on board, such as lettuce, which are really easy to grow. To provide power, we're going to need about 8.4 kilowatts of power at peak at all times. To do this when we're so far away from the sun, we're going to need approximately 42 kilowatts if we were in Earth orbit. Naturally, we won't be deploying all the solar panels at the start. As we go further out, we'll deploy them and then retract them as we come back on the return arm. We'll also need some batteries for when we're in the dark side of the Earth or on the dark side of Mars. To control the attitude of the spacecraft, we'll be needing a number of sensors. Our main ones we're using are sun sensors and internal guidance systems with star tracker systems acting as a backup. To control all of this, we'll then have two modes, either the gravity spin mode or 3-axis stabilization. To do this, we shall use momentum wheels, which will adjust the attitude of the spacecraft as we go through our cruise. And when we need to provide desaturation or a faster turn, we'll use the automated transfer vehicles attitude control thrusters, as well as the fuel tank on board, which is about 1.7 metric tons of fuel. To communicate, at our furthest, we'll be 3 astronomical units away from Earth. This will provide a delay of 25 minutes each way. Our main communication will be through the KI radio band, which will provide the main data uplink and downlink. We'll also have an additional X-band communication system, which allows for sensor and telemetry data back and forth from Earth.
1 minute.
To do all this, we'll be using the Deep Space Network, and when we're in eclipse with the sun, we'll be using Mars satellites as a relay. Just briefly, a thermal control system will be a mixture of passive and active systems. We'll be using a deployable ISS derivative radiator, as well as an internal heater when things get cold. This is a very sensitive system to design changes, so I've left it at the last. Thank you very much for listening. I hope I haven't bored you too much.
Time for one quick question. Tony.
Sure.
Do you anticipate any problems with when you're in artificial gravity, but the ATV and the MPLM are designed for microgravity?
That is a concern, but I figured if we apply some structural reinforcement to those modules, we should be able to counteract those problems. Both modules, however, have to be designed to sustain G loads when they're launched from launch vehicles, as well as moving around on Earth. So I imagine the structural requirements to reinforce them to a suitable point isn't actually going to be too difficult, but the joints between them could be, that would be the most problematic there, especially with the Earth return vehicle.
How about the crew getting to the different parts?
Yeah. Thank you.
All right, thanks.